How NASA's annealing trick saved JunoCam at Jupiter. Prepare to be amazed by how NASA turned a potential mission-ending disaster into a triumph of ingenuity. In August 2011, the Juno spacecraft began its ambitious journey toward Jupiter as part of NASA's New Frontiers program. Originally slated for a 7-year mission that included nearly 5 years of interplanetary travel, Juno's mission has been extended, allowing it to continue orbiting Jupiter and providing valuable scientific data well beyond its initial timeline. Among Juno's suite of instruments is the JunoCam, a visible light camera and telescope crafted to capture breathtaking views of a gas giant. However, Jupiter's harsh radiation environment posed a severe challenge to the camera's longevity. Many experts feared that this relentless radiation would inevitably lead to the failure of JunoCam. But here's where it gets controversial. Against all odds, NASA engineers have developed and tested a repair technique that could extend the usefulness of spacecraft instruments in extreme conditions. As the spacecraft completed several dozen orbits, 4 exceeding its original plan of 34 encounters, the damage from radiation became increasingly noticeable. The critical question was, what exactly was being harmed by the radiation, and could anything be done to prevent or reverse the damage? Detailed analysis revealed that while the image sensor itself remained intact, a voltage regulator within the camera's power supply was suffering from radiation-induced degradation. To combat this, the engineers opted for a process known as annealing, which involves heating the affected component. By cranking up one of JunoCam's heaters to a warm 25 degrees Celsius, a significant boost above its usual operating temperature, they aimed to repair the malfunctioning voltage regulator. This bold move initially yielded impressive results, with subsequent orbits showing dramatically improved image quality. Yet, almost as quickly as the recovery began, the quality started to decline again. Faced with the impending approach to Jupiter's moon Io, the team took another daring step. They increased the heater's intensity even further, figuratively cranking it up to 11 and crossing their fingers. Remarkably, over the course of a week, this intensified annealing process restored the camera to near pristine condition, making it seem almost as good as new. This innovative fix not only salvaged JunoCam, but also offers a promising blueprint for extending the life of other spacecraft instruments that face similar challenges in deep space. And this is NASA's ingenious fix, saving JunoCam 370 million miles away from Jupiter. Imagine repairing a camera 370 million miles away in the harsh radiation of Jupiter's orbit. NASA just did that, and the fix could change space tech forever. The Juno spacecraft's JunoCam, a color camera exposed to Jupiter's intense radiation, failed after 56 orbits. But engineers tried annealing, heating the damaged part to heal microscopic flaws. After warming it to 77 degrees Fahrenheit, the camera revived, only to fail again. Desperate, they maxed the heater. Days later, JunoCam snapped stunning images of Io's volcanoes, working almost like new. Why the drama? Juno's path through Jupiter's radiation belt damages electronics. JunoCam's outer placement made it vulnerable. Designers expected it to die after 8 orbits, but it lasted 34. By orbit 47, images corrupted. The culprit? A likely fried voltage regulator, crucial for power. With no spare parts, annealing was the last hope. But here's the controversy. Annealing's not fully understood. "We gambled it might work," admits Jacob Schaffner. It did, for a while. After a second, more aggressive heating, JunoCam roared back for Io's close-up. But by orbit 74, noise returned. Juno's lessons go beyond Jupiter. Principal investigator Scott Bolton says, "We're learning to build radiation-tolerant spacecraft, vital for Earth satellites and future missions." Critics argue annealing is a band-aid, not a cure. Can this hack truly future-proof space tech? Your turn. Would you trust annealing for a Mars rover? Share your thoughts. Learn more at https://www.nasa.gov/Juno. NASA's ingenious fix: how heat treatment saved Jupiter's JunoCam 600 million miles from Earth. Space exploration is fraught with challenges, But few missions have faced the relentless adversity encountered by NASA's Juno spacecraft. Orbiting Jupiter, a planet notorious for its harsh environment, Juno has had to contend with limited solar energy due to its distance from the Sun, communication delays spanning hundreds of millions of kilometers, and the intricate gravitational ballet created by Jupiter's massive pull and its 4 largest moons. Yet none of these hurdles compare to the sheer destructive power of Jupiter's radiation belts. These belts are so intense that they pose an existential threat to any spacecraft daring enough to venture too close. The culprit? Jupiter's colossal magnetic fields, which trap high-energy particles in a swirling maelstrom of radiation. This environment is particularly unforgiving for delicate electronics aboard spacecraft like Juno. To shield its critical systems, Juno carries a titanium vault designed to house its most sensitive components. However, not everything could fit inside this protective cocoon. One notable omission was JunoCam, the spacecraft's optical imager. While JunoCam isn't essential for the mission's core scientific objectives, it plays a vital role in engaging the public by providing stunning visuals of Jupiter's dynamic atmosphere. Over time, though, the unshielded camera began paying the price for operating in such a hostile setting. For nearly a decade, Juno has been circling Jupiter in a wide elliptical orbit that takes it perilously close to the planet's radiation zones before retreating to safer distances. Each pass exposes the spacecraft and JunoCam to bursts of damaging radiation. Initially, Malin Space Science Systems, the company behind JunoCam, predicted the camera would survive at least 8 orbits. Remarkably, it exceeded expectations, functioning flawlessly throughout Juno's primary mission of 34 orbits. But all good things must come to an end. By the 47th orbit, signs of trouble emerged. By the 56th orbit, JunoCam's images were marred by horizontal streaks and grainy artifacts caused by radiation-induced electrical noise. The culprit wasn't just the silicon-based CCD, charge-coupled device sensors used to capture light. It was also likely damage to the camera's voltage regulator, a component responsible for maintaining stable power supply. Faced with no way to physically repair the camera from Earth, the team turned to an unconventional solution: heat. Enter annealing, a process borrowed from metallurgy where materials are heated and cooled to restore their structural integrity. Engineers hypothesized that applying controlled heat might reverse some of the radiation-induced damage within JunoCam's electronics. They commanded the camera's built-in heater to raise its internal temperature significantly higher than usual, hoping this swashbuckling approach would work. "We didn't know if it would succeed," admitted Jacob Schaffner, a JunoCam imaging engineer. "But we have nothing to lose." Against the odds, the gamble paid off. Within days, JunoCam started producing clear, crisp images once more. This newfound clarity allowed the spacecraft to capture breathtaking views of Jupiter's storms, and even deliver sharp images of Io, one of Jupiter's volcanic moons, during a close flyby in December 2023. The success of this technique opened up new possibilities, not just for JunoCam, but potentially for future space missions facing similar challenges. However, the battle against radiation is far from over. As Juno continues its extended mission, now exceeding twice the number of orbits planned in its original timeline, JunoCam's issues have resurfaced. The team remains undeterred, experimenting further with the annealing techniques to prolong the camera's life. Meanwhile, lessons learned from Juno are already influencing how engineers design spacecraft destined for extreme environments. Juno is paving the way for future missions, said Scott Bolton, Juno's principal investigator. Its resilience in the face of Jupiter's radiation offers valuable insights for protecting satellites orbiting Earth and beyond. But here's where it gets controversial. Could annealing become a standard feature in spacecraft design? Or does it merely delay the inevitable? What do you think? Should we focus on developing entirely new technologies instead? Share your thoughts below. We'd love to hear them.